Okay, so we'll get started. So everyone, welcome. Thanks for coming to our symposium for our inaugural predoctoral student class. I'm Chris Hayward. I wanted to say, so I scheduled it so it's rather tight on time, so I'm just going to ask people, please hold your questions until the Q&A session, a couple minutes after the talks, rather than the usual sort of interactive talks, just because they're only 20-minute talks. We want to let the pre-docs get through what they want to present to us. We're going to go in alphabetical order. So first up, we have Irina Butsky, who's been mentored by Drummond Fielding and myself. And she's normally a student at the University of Washington working with Tom Quinn. She's been working on the impact of cosmic rays on the CGM. So Irina, please.
Awesome. Thanks. Can everybody hear me? Okay. So I'd like to start out by saying thanks for the organizers of this program. This has been a really amazing experience. And a special shout out to Drummond and Chris for being really awesome mentors. I've really enjoyed working with you. So without further ado, I'm going to talk about thermal instability and the role of cosmic rays in shaping that thermal instability in the circumgalactic medium. So the circumgalactic medium is loosely defined to be this diffuse gas that extends from the galactic disk out to the virial radius of a halo. And the majority of galactic baryons actually are in this halo, not in the disk. And even though it's really diffuse, the CGM has a really rich density, temperature, and metallicity structure that's shaped by outflows from the galactic disk and inflows from the pristine IGM. And I'm particularly interested in studying the cool phase of this gas, which is really important for star formation, because galaxies need to accrete cool gas in order to stay alive. And any cool gas that's accreted either comes from the CGM or at the very least must be accreted through the CGM. Now, people have been thinking about the CGM for a really long time. People like Ari, who's in the audience. And they made predictions for the structure in the CGM, specifically looking at the phases of the gas and making predictions for the density profiles as a function of radius from the center of the galaxy for different gas phases. So here is predicted electron density for cool gas and predicted electron density for hot gas. Now, when we were finally able to get lots of data on the CGM using UV spectroscopy from missions like COS Halos on the Hubble telescope, well, good news is we saw lots of cool gas. There's a ton of it. It's around all type of galaxies, including galaxies that are massive and quenched. So they're not forming stars, but they have tons of cool gas. It extends out to very large radii. So great, the cool gas is there. But it's also really weird in that it's extremely low density relative to what we'd expect. So if the gas were in pressure equilibrium, it would have this density, let's see, but it's about 30 times underdense, which is really puzzling because it implies one or two or a combination of these two things that if this gas really is out of pressure equilibrium, then it's likely to be very short-lived, which means there must be some sort of physical mechanism that can produce vast quantities of this gas on quick timescales. Or maybe there's some form of non-thermal pressure support, like in cosmic rays, that is supporting this gas against pressure. And so I'm really bummed this doesn't work. Okay. Simulations have strived to reproduce this structure of the galactic halo. And so when the observations of the CGM first came out, these simulations, which had been meticulously calibrated to reproduce the structure of the galactic disk, really struggled to reproduce the structure of the CGM. And now we're much closer. I think simulations in general do a pretty good job of reproducing, say, the metallicity structure or the phase of the warm gas in the CGM, but not so much the structure of the cold gas. And this is likely because simulations don't do a great job of reproducing or of getting good resolution in the halo, because traditional AMR techniques often add resolution based on density, and the CGM is really, really diffuse. So there are a handful of simulations in the last year that said, well, what happens if we increase the resolution in the halo, like by 10 times what is typically the resolution. And what they found, well, they made some beautiful simulations that did a great job of reproducing, or better reproducing, this cold gas structure. They're better at producing the observed quantities of cold gas, but these results don't converge with resolution, even at 10 times what the typical resolution is. And so I wanted to think about, like, well, what would it take to maybe incrementally add resolution to these simulations? So this is a figure taken from Evan Schneider that plots a handful of well-known galaxy simulations on a map of resolution on the y-axis and the number of volume elements on the x-axis. And so the simulations from this last slide would be somewhere in this region. But cool gas is predicted to have structures on sub-parsec scales, which is here and above. And a typical L-star galaxy has a halo that's maybe, or has a radius of about 200 kiloparsecs. And so if you wanted to actually resolve that, you'd have to go all the way out there, which, if you have a hard time reading this, is about 8 orders of magnitude more volume elements than the illustrious TNG runs. And so needless to say, that is not feasible in the near future. So there's a strong need to use idealized simulations to study cold gas physics and to understand it, and then take this better understanding and to inform galaxy scale simulations. And so what I did for this project is just that, used an idealized setup to study the formation of cool gas in a galaxy halo through thermal instability. So thermal instability in a stratified plasma works something like this. So if you have gas that's a uniform patch of gas in hydrostatic equilibrium with a gravitational potential pointing down, if you don't have any cooling and you get a small perturbation like this, what's going to happen is the cold, dense clumps are going to start sinking. The hot clumps are going to rise until the buoyancy forces are neutral and this perturbation is washed out. But if instead you had strong cooling, what would happen is this initial perturbation would start to grow. So the cold gas clumps would cool faster than the warm gas clumps, and that would make them denser, and that would make them cool even faster. And so you get this runaway cooling until you get a multi-phase medium where this cool gas is a distinct phase from the hot gas. And this process has been studied extensively in the hydro-only case, with magnetic fields, with conduction, with turbulence, you name it. But it hasn't really been studied in the presence of cosmic rays. And so cosmic rays are charged particles that are accelerated to relativistic velocities in shocks like supernovae. And they're an important part of the energy budget in the galactic disk. And they're very likely an important part of the energy budget in the galactic halo as well. And so there have been a number of simulation works, looking at how cosmic rays really change the density and temperature profiles of the CGM specifically. And so this is a very realistic schematic of cosmic rays moving around magnetic field lines. And so even though they're individual particles, on the scales we're dealing with, they're actually pretty well approximated as a fluid. And so this fluid can do a few separate things. Let me back up a second. So they're modeled as a relativistic fluid that's a second fluid on top of the traditional thermal fluid in the galaxy. And so it interacts with this thermal fluid in a few different ways. Specifically in a few different ways that have direct implications for the thermal stability. So first of all, cosmic rays offer non-thermal pressure support, which would take these cold gas clumps and it would make them less dense, so they would be larger physically. And depending on how strong this non-thermal pressure support is, it can prevent the cold gas clumps from sinking down in the gravitational well. Secondly, cosmic rays don't just move with the gas, they can move relative to the gas through either diffusion or streaming. And this can do one of two things. So one, it would alleviate some of the pressure support that cosmic rays have, because cosmic rays move down their density gradient, so they remove peaks of extreme cosmic ray pressure. And as they move, they actually drag the gas along with them, so it's likely that the velocity signatures of the gas might change with cosmic ray transport. And lastly, cosmic rays that are streaming can impart momentum onto the thermal gas and heat it. And I colored these the cold gas blobs a little lighter to show heating, but it's not necessarily straightforward. Like the mechanism, the way in which that they would heat this gas isn't straightforward to me, because the heating depends on the cosmic ray pressure gradient and the alphane velocity, which is a function of density. And you can have complicated effects like cosmic ray bottlenecks next to cold gas clumps. And so this is something that, well, we'll study in detail later. And so the simulation setup that we made to test this problem is a tall, skinny box of a gas that starts out in hydrostatic equilibrium with a gravitational potential that points towards the midplane. The box is 4 scale heights tall, and the gas is perturbed with a small density perturbation, or a small isobaric perturbation. And the cooling time everywhere in this box is constant. So we have a very idealized cooling prescription. So here the cooling function is just a power law of the temperature that cuts off at some minimum temperature so we can control over the minimum size of these clumps. And at every layer, or at every vertical layer, the heating balances the cooling. So, which is really important to keep global stability, so you don't just have the gas cooling and, so that you don't lose your atmosphere to runaway cooling. But the cooling is a function of density squared, whereas the heating is a function of just the density. So you still get thermal instability. And the simulations were run with ENSO, which I'm sure many of you are familiar with. And so before I came here, I implemented anisotropic cosmic ray physics in ENSO. And so I was really excited to continue that work with this project.
And you have the cooling and heating law, but you said there's a balance at every layer?
Yeah.
So does that mean you have like a free parameter or something that you're tweaking at every layer?
Sort of. So at one vertical layer, the cooling is dictated by this. Okay. And then we sum up all the energy lost to cooling and redistribute it to heating.
I see. You're conserving energy at certain.
Yeah. And so without further ado, here is a simulation of thermal instability in action. So there are no cosmic rays here yet. This is a density slice. And the difference between the simulations is the cooling time. So on the left, you have simulations with fast cooling. On the right, you have simulations with slow cooling. And I should add the caveat that these simulations are run for a constant number of cooling times, so 10 cooling times, which means that the simulation on the right is moving for a longer amount of physical time. And so as the simulation runs, you can actually see these cold gas clumps precipitating out of the hot halo and falling down onto the midplane. And this behavior is very nicely summarized with this plot. So this is the density fluctuation as a function of time for the 4 different panels you saw on the previous slide. And so you see runs where the cooling time is short relative to the gravitational freefall time, follow the predicted linear growth very nicely for about 4 cooling times, at which point they saturate, and in some cases they start to decay because the measurements are taken at the scale height. And so, this is great. But moving forward, I'm going to zoom in on this simulation with T cool, T free fall equals 0.3, and we're going to add cosmic rays.
Why is it so close to symmetric?
The perturbations are
the
symmetric.
perturbation was symmetric.
Yeah. And so now, these simulations are all at the same cooling time and free fall time, but we've added cosmic ray pressure. And so the cosmic ray pressure is initialized to be a constant ratio of the gas pressure everywhere in the simulation box, which means that for simulations where there's high amounts of cosmic ray pressure, the cosmic ray pressure support and hydrostatic equilibrium really puffs up the gas density. But I will kind of drive the point home one more time that they all have the same cooling time everywhere. And so when the simulation runs, you see that visually, when you have a lot of cosmic ray pressure, these start to look pretty different. So with added cosmic ray pressure, you see that the gas clumps are physically larger than they were before. The density contrast is lower, and they're not falling down towards the midplane. And so if you were to look at the same plot from the last slide of the density fluctuation growth over time, this basically says what we just saw, right? As you increase in cosmic ray pressure, you lose that density fluctuation growth. And on top of that, you lose mass flux. But if instead you look at the cold mass fraction at the midplane instead of the mass flux, you see that there really is basically just as much cold gas at the midplane as there are and runs without cosmic rays. And so can look at the temperature movies instead, and we see that even though the shape of this perturbation looks very similar to the shape that the density perturbation had, the contrast is really high. So you really see a lot of cold gas in all of these simulations. And so what this looks like, if you look at the probability density function, is remarkably similar for all of these runs. So yes, there are some slight differences, but this isn't something that would, motivate rethinking how we modeled the circumgalactic medium. But if you look at the density PDF, that tells a really different story. So in the run without cosmic rays, you see that there is a very distinct bimodality in the densities for the cool and hot gas phases. And as you add cosmic ray pressure, that bimodality shrinks until you get the very extreme case of very high cosmic rays, where this basically, there's a single density phase. And so this, so far we've just talked about cosmic rays with advection. So the cosmic rays have been moving with the gas without any transport. And so we're going to zoom in parameter space one more time and look at the run where initially the cosmic ray pressure is equal to the gas pressure and see what happens. And so now all of these simulations have T cool over T free fall equal to 0.3. They all have cosmic ray pressure equal to gas pressure, except for this one, which doesn't have any cosmic rays. And they differ in their transport approximations. And so advection is really just a test case that doesn't have any cosmic ray movement around magnetic field lines. Diffusion and streaming are both approximations to how cosmic rays move around magnetic field lines. And they're both physically motivated for different gas properties, but it's still kind of contested in the field as to which one or which combination of the two with what diffusion coefficients, et cetera, is a really good, or is the best approximation for modeling the circumgalactic medium. And so simulations like this will really help constrain that aspect of it. And then in the last panel, we have streaming with heating. And so in the streaming prescription, cosmic rays always heat the gas. But in our idealized setup, we balance cooling with heating. And so in this case, we choose to add an additional perturbative heating term, if you will, that follows the streaming prescription. And so if you let the cosmic rays move around magnetic field lines, all of a sudden this dramatic impact that the cosmic rays had before is reduced. But it's not all the way reduced. There's still a difference in the density PDF, but this is going to take a lot more work to kind of unpack, because you do see differences in the peaks of where the density, the peaks of the predicted densities for the different phases. You see these peaks have different widths. These peaks are also a function of the time in the simulation. So this one was at 5 T cool, and at 8 T cool is spread even farther. And so moving forward, we're going to spend a lot of work looking into specific predictions for different modes of cosmic ray transport and how those predictions are sensitive to choices like diffusion coefficient or the magnetic field strength. And so, in summary, I think cosmic rays are a really promising avenue to explaining this underdense cool gas in the CGM. And moving forward, so in addition to doing this parameter study of cosmic ray transport, we're going to develop an analytic framework to kind of make sense of some of the results we have seen. And we're going to do a resolution study. So the simulations I've been showing you so far have a resolution of about just under a kiloparsec, which is great for running hundreds of simulations with low costs. But as I mentioned before, cool gas operates on subparsec scales. And so I'm going to leave you with this simulation that increases the resolution by, I think, 200 times or 20, a lot. Yeah, so thank you.
What cosmic ray physics are in this simulation?
There are no cosmic ray physics in this simulation.
Is there a reason for that? That is to say, does including cosmic rays dramatically impact the computational cost or time step restriction or anything like that?
Yeah, there are a lot of great answers to that question. So this is the only really high resolution run I've run so far, and it doesn't have cosmic rays just because I know this is like the base run I want to have a high resolution of. In the version of cosmic ray physics that's implemented in ENSO right now, it has a traditional approach to diffusion and streaming, which has a delta x squared dependence on the time stepping, which does slow things down a lot. So we've been working at implementing the two-moment method, which doesn't have that time constraint, but it's not ready for this.
We're just going to swap out computers.
Yeah.
You opened with the observation that the density is low, and I just wanted to ask, how solid are those observations? Like, in two senses. One is it possible that since things are like complex, turbulent, and multi-phase, that those observations are kind of naive density estimates? And the second component of it is, are you planning on moving into a plane where you can actually predict the observations kind of more directly?
Yeah. So my understanding is there is some pushback against those observations, but that prediction is very robust to like lots of different turbulence, different UV backgrounds, and so I think even in the best case, it would still be about a factor of 10 under dense. And so I'm not sure about, well, making predictions more directly from observations can be tricky, but so I've been working with Jess to do synthetic spectroscopy, which can actually make those predictions for observations. So hopefully we'll apply that to this. Yeah.
On the other side of the same coin, predictions from that theory are also seem very high. Like even in the hot gas, the observed different tracers of the Milky Way hot gas have densities a factor of 10 or 100 lower. So maybe that would also resolve some of the destruction.
Yeah, I think that's a great point. The cosmic rays would do the same for the warm or the hot gas.
Okay, thank you very much. Yeah, let's thank Renee again. All right, and so next up we have Chris Duckworth from the University of St. Andrews, and while at CCA he's been mentored by Shai Ganel. Take it away.
Thanks. Is the volume okay? Great. So if this was sort of a realistically proportioned description of my time here, it would be about 40% slides on job applications. But what I hope to sort of give you a description of is some work that I've come here and finished, some work that has come out of nowhere and really has just come out of being at the CCA and just discussing informally with people, and finally, of course, a description of the project that I came here to do. So fortunately, I've had a very patient advisor in Shai who's struggled through me juggling all of these things. But a big thank you to him and, of course, everyone that's organised this program. So I'm going to be talking about angular momentum in the context of galaxies other than our own. And people have probably been saying this for decades, but I think we're at a really exciting point, certainly for exploring the angular momentum content of them. So on the observational side, we have large-scale IFU surveys such as MANGA. So an IFU is spatially resolved spectra. So the basic premise is you take a bundle of fibers, you plug them onto an observational galaxy, and you get both spectrum from the inner parts and the outer parts, and you can start to construct radial distributions. On the other side of things, we have large box cosmological scale hydrodynamical simulations of the order of sort of 100 megaparsecs that are at the point where they reproduce more observational properties that we see than we don't. So the caveats are far outweighed. So we're in this really exciting point where we can combine the two, check that the simulations are doing the right things, and trace back the formation. So I'm going to be spending a lot of time talking about something called kinematic misalignment. And the premise is pretty simple. So what I have here is an observation, an IFU observation. So on the left-hand side, you have the photometry, so just the image of the galaxy. In the middle, you have the velocity field for the whole stellar continuum, so that you can think of this as the rotation of the overall galaxy, so all population stars formed across times. And on the right-hand side, this is the ionized gas. So you can think of this as the newly forming stars. And so this ionized gas gives us some information about whether the more recently accreted gas is different to the previous stellar populations. So if you take your thoughts on tidal talking theory, if you take your thoughts on your expectations of tidal talk theory, you'd expect these two things to be rotating in the same direction. But on the other hand, if you have gas that is decoupled from your stars, then it's telling you something about the recent evolutionary history of the galaxy. It's telling you that something internal or external has disturbed the ionized gas and perturbed it away from the expected rotation of the overall galaxy. So this split 30 degrees is kind of arbitrary, but what it does is it takes into account all the typical errors with position angle fitting in terms of the rotational axis, and says that these are fairly well coupled, and these above 30 degrees are significantly decoupled. So I've shown you two examples of sort of an aligned and a misaligned galaxy, but there's a whole host of features that you can see in velocity fields, so they're not all well behaved. So for example, you get components that are entirely decoupled in the middle, just in the stars. You get components that are warped with respect to their outer parts, so you can see this is a bar in a galaxy. And one that I really want to sort of focus on and compare to later on is this special kind of galaxy that has coherent rotation in the stars, but quite a messy ionized gas velocity field. So it's thinking that something's depleted or there's no coherent rotation. So I'm now just going to tell you some general properties about misaligned galaxies in observations. So the x-axis here is delta PA, so the difference in position angle rotational axis between the ionized gas and stars. And it's a PDF. Now, excusing the strange units, the takeaway point here is that 90% of galaxies fall in this regime here, below 30 degrees, what we're normally calling aligned. But extending past that, you can really start to see this morphological dependence. So galaxies that are earlier typed, i.e. redder, more dispersion dominated, have a higher proportion of galaxies that are misaligned. So about a third of them show this decoupling. Whereas on the other hand, if you have something more spirally, it falls down to about 5% of the population that are misaligned. So there's a strong morphological dependence and relationship with the visual morphology and the likelihood of the misalignment.
And to make that plot, did you have to remove a lot of ambiguous cases? Because you showed some cases that looked ambiguous. Did a lot kind of get cut out of here, or do you always deliver a delta PA?
No, so you throw away about half of your galaxies.
I see.
So for rough numbers, we start off with 6,000 galaxies. About 3,000 of them fall into one of these two categories. and then about 750 or so fall into this category, which I'm also going to mention. The rest get removed. And there is certainly a bias there towards earlier morphologies. So
how surprised should I be at this? I mean, obviously the older galaxies have had a merger, right? And
yeah.
so things might still be moving around inside, or there might, so isn't this exactly what you would expect? That the early type galaxies that likely had mergers have more disturbed gas and things inside them than, younger galaxies?
Yes, but I'm going to continue on with the things that you'd expect before talking about things that you might not expect.
Okay.
Okay?
Let's actually, since we only have 20 minutes per person, let's try to keep the questions to the end.
Okay.
Okay, so continuing along these lines, so this plot here, this is going from lower specific stellar angular momentum to higher specific stellar angular momentum, and this axis is a sort of measure of the 2D projection of the flattening of the galaxy. So things that are typically more round fall in this regime, things that are typically more disk-like fall in this regime. So all of the individual points are galaxies in the Manga survey that we can define a delta PA for. And then the colored lines here refer to the medians of our different categories. And so something that you can pick out, and as Chiara mentioned, it's expected that you have the misaligned galaxies be at typically lower angular momentum, and they're typically rounder because they're more earlier type, compared with the aligned ones that take up a bigger fraction of later spirals. So that's not particularly surprising. And also, if you're looking at the gas content of these objects, is that the misaligned objects typically have a lower gas fraction, a lower gas mass overall. Now, what's a little bit more interesting than that is that if you remake both of these plots, but just selecting purely on morphology, so if you make this plot purely for elliptical types, purely for spirals, purely for lenticulars, you recover these individual trends. So all of these lines shift around a bit, but the qualitative trends remain true. So keeping that in mind with a few primers of what we see in observations, our next step was, how do we get there? And as I mentioned at the start, a real good way of doing this is comparing two cosmological simulations. So we went to illustrious TNG, and for every Manga galaxy, we picked out an object that looked most similar, and then made what I call a quick and dirty observation of it. So something that would roughly give you the stellar velocity and the gas velocity mixed in with the typical observational noise that you'd expect from Manga observation. So now at this point, we can start thinking about tracing back the evolutionary history of these objects. But first of all, we should probably start with a sanity check. So do we even reproduce this distribution that we saw with respect to misalignment? And so first, starting with the caveat, is that the overall shape of the distribution is slightly different. We have a sort of higher bias of objects towards this misaligned end, and I can talk about the details later as to why. But the really great thing is that we're recovering this qualitative trend with the quenched and star forming, despite all of these sort of non-perfect observations and all the other factors that go into this. And even nicer, we're recovering sort of secondary order trends between centrals and satellites, which I won't talk about now. So we're doing a good job. So something that just came out of the blue in discussions and being at the CCA is we took a look at the relationship with the AGN in galaxies and just in illustrious TNG at the low mass end. And so what I'm plotting here, so just focusing on the top row, is energy injected, and then this axis is going from redshift 0 backwards in time to 8 gigayears. So this is a relative quantity. So the grey dotted line here is all of the aligned galaxies less than 30 degrees, defined relatively to the misaligned galaxies. So you can see, in comparing the two, there's an excess in the energy injection from the AGN for our misaligned galaxies. So the misalignment is defined at redshift 0. We trace back the energy injection. We see that there's a richer history of energy injection from these misaligned objects. And you also see this if you look at the excess of the black hole mass. You see a certain excess and a linear growth towards redshift 0 of these objects for all morphologies at redshift 0. But another interesting point to point out is that if you bin these into quenched green valley and star forming at redshift 0, so just selecting on a specific star formation rate, this sort of peak in the energy injection from the AGN is at a different time step. So it's telling us something about the relative time scale. So for the star-forming galaxies, it's had more recent energy injection from the AGN, going green valley a little bit further back, to the quenched a little bit further back even more. And you can also see that reflected to a certain degree in the black hole growth. So it's telling us something about the processes that's going on here. So combining this in with some information from observations, there's a clear relationship with mergers leading to this misalignment, but doesn't tell us the full story. You can start to build up a picture, at least for the low mass galaxies, as to what's happening when we take an observation at a given time. So you can think of the first scenario. So here, this is just a rough clump, galaxy clump, and the hexagon is the IFU footprint, if you mode it in Manga. And so this is the stars and the gas, and your usual expectations, these things are all nice and aligned. You continue forward in time, and you have something that happens, say a merger. And what this does is it disrupts the angular momentum, as you'd expect. It causes the gas to decouple from the stars because, you might have an interaction that strips gas out or talks it differently to the stellar population. And this leads to more gas inflow towards the black hole. So going forward another time step, for the low mass galaxies in illustrious TNG, this was then seen by this energy injection that you saw in the previous plot, and leading to this radiative outflow and then the gas loss that we saw for the trends in observations. And the point to be made here is people in observations have taken all of the misaligned galaxies and then correlated it with the AGN luminosity and gone, look, there's no correlation. But the point we were trying to make here is that depending on along this time scale, when you make the observation will entirely dictate whether you actually see a correlation or not, because the misalignment is lasting throughout this process. So if you make it here, then obviously it's aligned. There's no AGN luminosity or feedback. If you make it around this zone, then you will see a correlation. And keep in mind that this AGN feedback will lead to quiescence as it quenches the gas, heats the gas. However, if you make it further on in time, where these galaxies remain misaligned, you're well down out of the way where the AGN is really contributing to or suppressing the star formation. So just taking a little bit of a sidestep and going back to talking about angular momentum, is I mentioned that the stellar angular momentum is lowered for these misaligned galaxies, certainly just instantaneously at the redshift 0. But this holds true if you trace back all the way back to redshift 1, sorry. So, sorry. I'm not sure what's happened. Okay, great. So on this plot, again, okay. Lovely. Okay, so again, we're going from redshift 0 here, backwards looking in time. So this is actually the same time scales going back to 8 gigayears, just in different units this time. And so again, thank you, we're splitting on the star formation rate at redshift 0. and also splitting into aligned and misaligned, you can see that in all cases that you have this lowered angular momentum at redshift 0 for these misaligned objects of all morphologies, but also that the ensemble average for this population is lower, going back to at least redshift 1. And even further, rather than just looking at this IFU observation, so within about 2 RE of the galaxy, and consider the angular momentum of the whole subhalo, it's reflected there as well. And there's no real significant evolution from redshift 1, so the probability of misalignment at redshift 0 is sort of reflecting a more fundamental property. And so this sort of leads nicely into the work that I came here to do with Shai. And so now, forgetting about the kinematic misalignment for a second and just considering about the overall magnitude of the angular momentum in the galaxy, this can also be described in the coherence or the alignment between the angular momentum vectors of different components. So what I'm plotting here is, again, a PDF for a distribution of galaxies, or about 300 galaxies around 10 to the 12 in group mass, so roughly Milky Way size. And I'm showing the alignment, the cosine angle alignment between different components. So J galaxy is roughly what we see inside the IFU observation. And if you correlate this angle with all of the stars in the halo, so including CGM, etc., you really start to see this dependence or relationship with the total angular momentum magnitude of the galaxy. So these higher spin galaxies are the ones that have more coherent rotation, not between just the gas and the stars, but also the outer parts that you see that you wouldn't pick up in the IFU. And even further, this is also seen in the coherence rotation between the dark matter. So it's not just a form of coherence between the magnitudes of the angular momentum, it's also in terms of the direction. And so that was all just considering at redshift 0. But what happens if you take all of these resolution elements and consider the alignment between these different components and the initial conditions? So this is going back to about redshift 127. And what's quite amazing is that you still recover these qualitative trends. So for the material that becomes all the stars in the galaxy at redshift 0 and the material that sort of becomes the outer parts of the stars in the outer halos, they're quite incoherent for these lower spin galaxies, but they are far more coherent for the higher spin galaxies. And this is also true, again, if you're looking at the coherence between the dark matter. And so you can sort of express the angular momentum of the galaxy at redshift 0 in terms of how much these different components, the angular momentum vectors, reorientate over cosmic time. So these galaxy stars, all of these resolution elements that go on to form the stars at redshift 0 are very sort of randomly orientated over cosmic time for these low spin galaxies at redshift 0. However, for the ones that form these higher spin galaxies are the ones that are retaining their direction in terms of angular momentum. And this is also reflected in terms of stars outside of the IFU and for the overall dark matter halo. So I'm just going to leave you with my summary slide and conclusions, but again, I'd just really like to thank all of the organisers for this programme, and David, and of course Shai, and thank you for having me.
Thanks very much, Chris. Questions? Yeah, all right.
Your previous plot, are those for halos and or galaxies of the same mass, or is
This one?
Yeah.
Yeah, so they're all for all groups that are roughly 10 to the 12 in solar mass.
Have you had a chance to look at any other mass?
No. Yes.
You showed a slide about the AGN feedback in black hole growth. And your black hole, your black hole growth looks really smooth. So if I were to assume that there had been some supermassive black-hole merger happening, I would expect to see a step function, right?
Yeah, so I think.
So do you mean that? So what can I take away from this in terms of the black-hole mergers?
So I think some of the information is lost in the fact that I'm showing you an ensemble average. So I'm taking all of these galaxies in a category, and they'll have different time steps of this merge happening. So if you took an individual galaxy and then plotted this, then you'd see that spike, but once you average over the ensemble, you lose that information.
All right. Okay.
But do have some plans to look at individual cases, which would be quite interesting.
I was surprised that there wasn't more of a peak in either the simulations or in the data. Basically, the agreement between the simulations and the data is remarkable. And I'm surprised there isn't more of a peak at 180 degrees. Because we know of these examples of counter-rotating. There's sort of these famous counter-rotating. And I sort of had this picture in my mind that counter-rotating is somehow a natural outcome of galaxy formation. But it looks to me like there's lots of, or are there ways? Anyway, I want that to be questioned.
So I can give an answer to that sort of question. So in the observations, something that's, I'd say, quite interesting is if you take your plate-type spirals, and so only 5% of them have a misalignment more than 30 degrees, but roughly half of those are in that 150 degrees and above category. Something that I didn't show there as well is that these counter-rotating objects have roughly the same angular momentum as the typical misaligned population. So I don't know if that is some insight into similar processes going on. It's creating quite a disrupted misalignment and then it's relaxing to this counter-rotating state. I'm not sure. Does that sort of answer the non-question?
Yeah, exactly. It does. It's very, very impressive that there's such a variety. It's really
so I would say we saw signs of recovering this little peak towards 180 degrees in the illustrative TNG, at least in some populations. But for other papers, I think in Horizon AGN, they didn't really see this. So it's still really hard to tell if simulations are reproducing these counter-rotating objects fully, but there's some. And I would direct you to Tosuke's Starkenberg paper.
Okay, let's thank Chris again, please. All right, so next up we have D.W. Han, whose home institution is Stony Brook, and while at the CCA, he's been working with both Sigurd and Simone. Please.
Thank you, and thank you for having me. And can everyone hear me? And before I go on, so Simone is not here. He's at Atacama, but he said it's nice message saying that I didn't know. I thought that was
I'm online, DW. I don't know if you can hear me.
How are you? So today I'm going to talk about some of the work I did on CMB cosmology using the observation data. And the technique and the pipeline we have developed here will be also useful for the future science case at the science project for the Simons Observatory. So this is just a schematic picture of the cosmic history. And I'm interested in this particular subchapter of cosmic history in the history of CMB. And the history of CMB traced most of the cosmic history. So at about 300,000 years after the inflation, the CMB is imprinted with the primary anisotropy. And as the universe expands and the large-scale structure form, it imprints the secondary anisotropy. In particular, for instance, weak lensing by the intervening matter, and by the photon are least scattered. CMB photons are least scattered by intervening matter in terms of thermal and KSD effect. And also by the time we observe the CMB, they are also contained by the foreground, both from the galactic and extragalactic sources. And CMB has been an active area of research for many years, and here I'm showing the three blue sky survey experiment, Kobe, WMAN, Planck. As you can see here, the improvement over the time has been very dramatic. And in particular, in the last year, the Planck released the last set of their science paper in 2019, concluding their very fruitful research science case. So, but there are still more to learn from CMB, especially with the ACT and the Simons Observatory, which is ground-based high-resolution CMB experiment. And here I'm listing some of the science cases. I just chose it what interested me most, but there are many, many more. In particular, I'm highlighting the top two the science case I've been working on mostly. The first one is what I have been working on at the Stony Brook and have been continuing working on here at CCA, which is studying the matter distribution using the CMB weak lensing technique. And the other thing what I have started exploring at the CCA is trying to understand the extragalactic astrophysics of extragalactic source you observe on CMB data. And why is that interesting? Why is that matter? Why is it interesting? It's interesting because our data are getting better and better. So this is a nice. This is a snapshot of the nice video that Cigar made, which showed that on the right-hand side, you will see the image from the Planck data. And you can see that they're nice, but they're kind of grainiest image. And on the left-hand side, you are combining the Planck data with the ACT observation of 2018. And you can see the images are much sharper. And also, you will notice that now you're seeing the small feature on this CMB temperature map, which is radio and submillimeter galaxy is observed in our data. And also, it's furthermore, ACT4 is observing, advanced actually observing large section of the sky. So not only we are trying to resolve all this source on our data, now we are observing large patch of sky, so we can make a comprehensive catalog of this source and do good, interesting analysis with this data set. Before I go on, all this work cannot be done with the work done by the collaborators, so I want to acknowledge their contribution. So ACT4 is located at Atacama de Chile. We observe the sky at 90 and 150 and 220 gigahertz. Actually, Simone is at Chile, helping to insert the lower frequency channel. So next season we have one more channel to observe that, and we observe the sky in both in temperature and polarization. And furthermore, I'm part of the Simons Observatory collaboration, which include all of the ACT member, ACT collaboration member, and the Polar Bear member, and many more scientists around the world. So in the near future, there will be no shortage of a great CMB, high-resolution CMB data. So let me start with talking about CMB weak lensing and the de-lensing of the CMB. So the idea is very simple. The CMB, so for the weak lensing, you need a backlight. In this case, your backlight is a primary CMB formed at the redshift of 1100, and by the intervening matter. So CMB lensing corner is peaked at redshift of 2, but it has very broad lensing corner. And by the time you observe the CMB, it's a lensing distorted. And weak lensing is a statistical anisotropy. So here I'm showing the nice slide made by Matt at Primary Institute. So below I'm showing the CMB temperature intensity map, on lens CMB intensity map. So this is a kind of picture you will observe when if there's no weak lensing. On the top left, I'm showing the power spectrum from this map. The blue curve, which you have to see here, is from the left half of the map. The orange curve is from the right half of the map. And see that when there's no lensing, they match the left side and right side match very well. But let's say now you're introducing over density mode to your CMB. And let me go back and forth a little bit. And you will notice that once I introduce over density mode, the right-hand side of the map is being stretched, and the left-hand side is being squeezed because the right-hand side of the map is overdense compared to the left-hand side. And you will also notice, if you now focus on the power spectrum plot, you will notice that the blue curve, which is where from the left part of the map where maps are squeezed, is moving toward the right. And the orange part is actually where maps are stretched, moving toward the left, which is conceptually easy to understand because you are moved on the left-hand side, you're squeezing the map, so you're moving power from the large scale to the small scale. So it's moving to the large angular scale, smaller angular scale. You're moving power to the smaller angular scale, and the opposite is happening when you're stretching the map. So it's moving to the left. And since CMB, this weak lensing mix the mode at different angular scale, and this mode mixing is proportional to the strength of your underlying lensing field at particular scale, this allows you to reconstruct the lensing field mode by mode. And since we are at CCA, let me talk about a couple of code I have been contributing. One is a FICON code, a fast AI lensing reconstruction code. This implements the Hu and Akamoto lensing estimator, and this has been main ACT lensing analysis code for which is used in Shorin et al., which have a lensing auto spectrum from data release 1. And the paper I'm working on, and so on and so forth. So this has been our main analysis code for the lensing. And right now it's private in the private repository, but maybe in the future it might become public. And once you have this pipeline and you want to verify and test with the simulation, so I was also very involved in the simulation effort for ACT. And this is called the ACT-Sim simulation. And this is Paul Lama, which is the mascot for the ACT-4 experiment. And this includes a set of simulation. You need to test the CMB lensing and realistic noise model for ACT, and other thing you need to simulate to test and work on the CMB data analysis. And currently it's in the ACT repository, but the set of simulation will definitely release once the set of papers are published. So here, so this is a simulation. Now, what does the reconstruction map look like when you actually apply to the data? And this particular map is made by Omar Danish at Cambridge. And this is an ACT lensing potential map. So this is a 500 square patch of the sky, and you apply the lensing reconstruction on it. So what you see is signal dominate lensing potential map. So what these blobs are actually, you're seeing the dark matter, which it doesn't look like much at this plot. But now if you overplot like CIB, which is also nice tracer of the same underlying matter density, you can see the contour match very well on this map, which means that this lensing map you have reconstructed is very high signal to noise. And as you notice here, you can do various kind of, since the CMB lensing kernel is such a broad kernel, you can do many excellent cross-correlation science with once you reconstruct the lensing map like this. But what I have been mostly working on, I have been helping with those projects too, but what I'm mostly working on is try to undo this lensing effect on the CMB field. So try to undo the lensing distortion. And there are many reasons why you want to do this, but the most people are most familiar with in terms of searching for primary B mode. So here I'm showing the primary gravitation wave generate the CMB primary B mode signal. So on the right-hand side, I'm showing the CMB BB power spectrum, and you can see this blue line is the signal from the primary B mode signal, possible we don't know the amplitude very well, so that's why there are the lanes to it. And you will see also the green line labeled lensing B mode. And so what lensing does is lensing converts CMB E polarization to CMB free polarization. And you will see that for most of the relevant scale that you can measure is this lensing B mode signature is much higher compared to this lensing, this primary B mode signature you want to observe. So this process removing the lensing-induced power is called the de-lensing procedure. And it's one of the main techniques to get to this signal of interest, impulational signal of interest. And there's other application of the de-lensing, but this is one of the main things people are interested in. And the idea of de-lensing is very simple. To the leading order lensing, weak lensing is you moving CMB pixel by the gradient of the underlying your lensing field, which happen in both the temperature and the QU polarization map. And so what you want to do is to the leading order, you want to reconstruct you make a lensing tracer of a true lensing potential. You take a gradient and you invert the gradient and you move back you undistort the map you have. So that's one way to to de-lens the map. And once you de-lens the map, next thing you always want to check is take a power spectrum. For CMB, first thing you do is take a power spectrum and check. And the code, this is another code I have been developing and maintaining, which is called the PDAS, which is the implementation of the curved sky to the CA algorithm to take unbiased CMB power spectra. And this code is publicly available for anyone to use. And other thing I have been doing while I'm here is to cross-check the spectra for the Choi et al., which is the main ACT analysis power spectrum paper, which will come out soon, and which is a power spectrum going to use for the main parameter paper, Aola et al. So those papers also will come out soon from the ACT collaboration. And this is some result from simulation. So on the left-hand side is a power spectrum of lens minus power spectrum of de-lens. So basically, this is constructed in a way that to see how much lensing signal you can remove. And this dotted line I labeled as a perfect de-lensing, which means that if you can de-lens your signal perfectly, you get this dotted line. And this orange line here I'm showing is expected de-lensing, how much you can de-lens with given the same particular patch. I've been looking at D56 patch from ACT. And you will see the blue dot is actually from the simulation after you actually process with this de-lensing procedure. And you can see that they match pretty well. And this one is some outlier. I need to take a look at it, but yeah, you know that this procedure is working very well. Yeah, 5 minutes. And there are much more detail, and there's actually we are processing also data, but those we release. We are hoping to release our paper soon, and more detail can be found at this paper that will come out hopefully very soon. And other thing have been so that's with the CMB weak lensing. So other thing I have been interested in working here is looking at the extragalactic source using ACT data. And the nice thing is that since we are scanning sky, scanning large section of sky, CMB observation detect this radio and the the radio and sub-millimeter galaxy for free. So this is also a nice map made by Sigurd. So you can see that there you will see all this small dot, which is, as I said, this is an extragalactic point source. And this map are not filtered, so if you want to actually filter the map in a way to find those sources, you will find many, many, many more sources, which I show the plot later. And these extra galactic sources are dominated by two types of galaxy. One is galaxies hosting the active galactic nuclei. And the other type, other flavors come as a dusty star-forming galaxy. So those two sources dominate our point source detection. And the one I've been working on is trying to build a catalog of these sources, like these galaxies, and analyze. And to that end, I have been building this crush pipeline. So it's still under construction under my repository. And it's interfaced with the NEMO pipeline, which is the ACT and SO pipeline for the point source detection. And yeah, NEMO, crush, you know.
My kids will love this.
And the goal of this pipeline is to allow the flexible, to build a database of this catalog and allow the flexible slicing. So that, for instance, if you want to track this particular source in temperature and polarization and different season, the goal is to be able to do that easily and for the best analysis. And here I think I put the link of the image. So this is an old plot I made a while ago. So the blue, each of the circle are the source you are detecting, and the color means your log of intensity of the source, flux of the source, and the size of the circle means signal to noise. So this is our season 13 data, which there are this small tube patch. In 15, you got a little bit bigger. 15, you got even bigger, so they have much more area, and you detect much more sources. And this is from season 16, which is our current observation footprint. And this is still need to be processed, so some of the sources will be cut, but we also and we even have better data for season 17 and 18, so we find many more sources, and it's going to be very interesting data to analyze there. And last thing I will mention is that we're doing all this work on the CMB data. What I have been started realizing is that the foreground is getting so foreground is getting more interesting because our noise level are getting lower and lower. So at the moment, the foregrounds are simulated as a Gaussian random field, which is fine if the noise level is high enough. But we are getting at the point where this foreground simulation and foreground modeling is getting more important. And there are only a couple of realization of realistic foreground. In particular, there's a Segarello from 2010, and about a decade later, there's this simulation from the website, which is, and websites still have some issue matching the observation. So there are not that many this realistic foreground simulation, the matching observation available. And I have started talking with Paco about it, and he has this magic black box machine learning technique you can use to go from this train on this simulation and make a many realization program simulation. I just started talking about this project with Paco, but it looks like it'll be very interesting. And as the noise level goes down, even for the Simons Observatory, I think it'll be interesting to have many of these simulation you can use. And this in summary, there's many science you can from CMB and the ECPO and the Simons Observatory. We provide high quality data, so there are lots of interesting science you can there, and you can extract the weak lensing information from CMB and try to de-lens underlying CMB, which is an important technique for the many future CMB science cases. And you can also detect this radio and subliminal galaxy for free, and you can build a catalog and study their astrophysics. And lastly, I just put it here. So we might be able to generate the more realization of realistic foreground using the machine learning technique, and still looking into this. And that's it.
Thank you very much, DW. Questions?
So when you showed where the point sources were,
yeah,
right, you got very clearly, isotropic map with lots of points near the edges of the map.
Mm-hmm.
Is that, I mean, do you understand, is that the noise? I assume your threshold depends on the local noise. So is it anisotropies in the mapping? Is it, what's going wrong?
So
Point sources in the universe don't know about our mapping strategy.
yes, so this NEMO pipeline we are using here to detect this point source is not good with at the edge of the map. So basically you're picking this random fluctuation as a point source. So for the main analysis, you probably need to cut out those parts of the data to analyze, to get this realistic, reliable source detection.
So if you throw out a couple degrees along each edge, is that enough?
I think you know it better.
Yeah, so I've worked a bit with in my own point source finding code, which is different from NEMO, but uses roughly the same principle. And it turns out to be very difficult to avoid having these false positives along the edges of the patches. And the reason for that is that the noise properties of the map usually vary smoothly across the map, but as you approach the edge, they start varying very rapidly because the telescope is turning around, and as it turns around, a lot more time is getting compressed into a lot less space. So you need very detailed noise modeling there, and it's only like, you're talking about like 20 odd minutes or something, and it's much easier to just do so what I do is that I just, first of all, you mask the galaxy and stuff, that's simple, but you just do a pass and you cut out the regions that are close to the edge, and that turns out to be pretty good quality. So this isn't a big problem, it's just a bit marring for the visualization here.
Right.
Yep.
Yeah.
Have you discovered any new galaxies, and have you done our cross-correlation search with other wavelengths to
Yes, that's something that was in the to-do list. So first, I want to finish the building catalog and process all these like edge case and so on and so forth. Once the data set is reliable, so next thing will be to just analyze it and also do the cross check against the other data set that's available.
Any additional questions? You want to get set up? So I was curious, do you have an estimate, like, or what's your flux limit for the point sources? So I'm specifically interested in just these star-forming galaxies. What's your flux limit, and what's roughly your expected number of sources, if you remember?
So yes, without cut here, the proper cut here, I think from season 16 data, I think I get 10,000 to 10,000. But I haven't made the cut yet, so after that will be reduced. But our data set for S18 are have much lower noise. So once I include the data, I think it will be But I don't have exact sense of how many I found. And do you have any data figures?
So you want it for advanced stacked or for Science Observatory?
I guess in the current data, so
Okay.
season, what you said 15 or something. I mean, we can talk off, we don't need the exact numbers, I was just curious.
For the current data, the 5 sigma detection threshold is roughly 5 sigma is roughly 8 millidans.
All right, so let's thank DW again, please. All right, so next up we have Elias Most from Goethe Universität in Frankfurt, and he's been here working with Sasha Philippon.
Yeah, thank you, Chris, and thanks for the nice introduction. So I want to talk in a little bit of a different setting about neutron star mergers, and in particular a new mechanism that we have kind of found like having a new observational window into the system before it merges. This is kind of relevant at the moment because we've just started to get new detections in for neutron star mergers. Just I think last week or 2 weeks ago there was a new detection reported. And so, because I'm not sure how familiar we all are with the subject, I'd like to first give some short introduction, like very brief, about what's the setting that we're talking about, what are the observational prospects, what is the kind of physics that we can learn from the system, then before going into more details on the recent work that we've done here at the Flatiron Institute. And so, since we're all doing computational physics, I thought instead of giving you like slides with words and everything, I'll just show you a nice movie, just how the merger of two neutron stars work. This is really their final fate. They're just about to merge and be disrupted. And this is a full simulation, so it's not an artistic movie. And what you see is now, or what you don't see, is the gravitational waves carrying out all the angular momentum and all the energy. And so over time now, the system is going to come closer and closer together until the stars finally touch and merge. And when this happens, a lot of dynamics is going on. It's really like smashing two balls of matter together. A lot of debris is flying out. We form this metastable object. And because the metastable object is not axisymmetric, it's radiating gravitational waves and ultimately then will collapse and form a black hole. And from these different stages of the merger, we can extract different information, and we have different observational tools in order to really access the physics that this is telling us about. And just if we want to put this in a cartoonish way, just to see, what are the different stages, what are the different prospects, like this is kind of the initial stage that we saw at the beginning. You have these two neutron stars orbiting. They start to emit gravitational waves. So this is indicated here in the in-spiral waveform. The nice thing about this actually we can detect right now using the LIGO detectors. This was the first detection, GW170817, that we've made of the system. And the interesting thing is now if we progress in the movie, so now when we have the collision, we form this hypermassive neutron star, and then as you can see, the gravitational waveform changes simply because the object becomes much more compact. So you go from the orbital size to the size of the remnant. And the interesting thing is that in a different life, when I'm not here, I actually work on how we can use this part of the waveform to learn something about matter at the most extreme and fundamental states, but this is not part of this talk. The other thing that you can do then when you collapse and form a black hole torus system, you get all of this matter orbiting the black hole, you have strong magnetic fields in there, and this will ultimately drive mass ejection. The interesting thing about this is that the system is not all about gravitational waves, because all the matter that is being ejected, and that we've seen also in the movie, like all the stuff that was flying out of the screen, is heavily enriched with neutrons. So this will form very heavy elements by our process nucleosynthesis. And the nice thing is the heat that is produced in this formation can be detected via kilonova afterglow. So this gives us a very nice electromagnetic counterpart. And combining all of this together, there has been a nice kind of result on constraining what nuclear matter looks like, what neutron stars look like, and so on. So this is kind of one of the other important windows that we have other than gravitational waves. And then this also produced a lot of nice elements, like this one that we all love and cherish. And finally, if you look in the black hole torus system, because this will have a strong magnetic field, it's a bit like the EHT observations of the M87 galaxy, where you have a jet. This system will also produce a jet, so there's really matter in the end coming out, not of the black hole, but basically being funneled, being ejected. And this gives us a nice short gamma ray burst that we have also observed. And so you see that instead of just having the gravitational waveform, you have two more channels, the kilonova and the short gamma ray burst, that we can study the system with. But obviously, there's something missing. And this is like specifically a line that you see there is like an empty white spot. So is there something more that we can learn about? And the point is, yes, maybe we have in the future, like, and Tom can tell you a lot about the observation prospects of that, we have another chance of looking into the system even before it merges. And this is because the neutron stars are not just orbiting in vacuum, but they have very strong magnetic fields. These two magnetic fields here, they can connect to each other, they can interact, and the interaction might produce a transient that is actually observable and tells us something about the binary parameters. And so this is really what I've been studying here together with Sasha, and we just published this week a paper of this. It will appear on Monday on the archive if you are more interested. I'd like to walk you through a bit on what is the parameter dependence, what is really the novelty about this, and what can that teach us about this system in addition to these other electromagnetic counterparts that already have been observed. And so the idea is the following. Before you can even start, let's just go back to the cartoonish picture. Let's be even more cartoonish and let's say, we didn't really see magnetic fields in the movie because it was just hydrodynamics, but let's paint on the magnetic field by hand. So you have these two stars that orbit with each other, and then you see that we add here by hand a magnetic field pointing up and a magnetic field pointing down. Because arrows are not so nice, let's draw some field lines, and this is really the setup that we will consider. So you have like one of the field pointing up, one of the field pointing down, and then we will see what kind of interesting effects like the orbital dynamics does with this field. And so before we, however, do any kind of simulation, we always have to go back to a pen and paper estimate. Is it even worth our time to study the system? And people have done this over the last decade or so. They have thought, like, what do we actually expect? And one of the most common estimates is that when the two stars orbit, you should get some continued emission of electromagnetic radiation, simply because you have a moving magnetic field that is going around. And this gives you about, for let's say, reasonably high magnetic field strength and close to merger, which is a separation of about 30 kilometers, say, a luminosity in the electromagnetic field of about 10 to the 42 ergs per second. The interesting thing is, and this is a bit like if you go to a lab and you talk to people using lasers, this is nice because that's a continued emission, but you'd like to have some more, because the more you have in luminosity, the more likely it is you can detect it, even if it's far away. And the simple thing that you do for the laser is you say, okay, well, I don't want a continued laser, I want a pulsed laser. So I store some of my energy, and then I release more energy. So the energy that I release over time is the same, but the power is kind of pulsed, and so it's higher. And that's exactly the thing that we did. So we said, okay, there's a fudge factor, and if we can get some kind of pulse emission, we can boost this thing by 2 orders of magnitude. So before I tell you how exactly this works, I want to say just 1 or 2 slides of the equations that we have to solve. And it all boils down to that the neutron star is not just a magnetic field and vacuum, because then we wouldn't see anything, but it's surrounded by a very highly conducting electron-positron plasma. It's really because the magnetic field strengths are so high that at the polar cap of the neutron star, you get a vacuum breakdown, you get your electron-positron pair cascade, and then you fill up the whole surrounding by this highly conducting plasma. And some of the things that this is doing, it's just if you take your dipole, it will basically result in the fact that your field lines have to open up beyond a certain radius because they can not co-rotate faster than the speed of light. It's if you think about it, a bit like them gaining in inertia. It's not the right way of viewing it, but it's a good way of visualizing it. And the interesting thing about this is if you study this in a single pulsar, because we actually know that this works this way, because we observe a lot of pulsar observations where you have a neutron star, your magnetic field is misaligned with the spin axis, and then when the neutron star is spinning around, you get like a beamed emission pointing at you from time to time. It's a pretty accurate clock, maybe the most accurate we have in the universe. And then you see that such a system forms a current sheet, and this is nothing but saying that if you have a field line going this way and a field line going this way, there has to be a current in order to support this configuration. And the nice thing is, and this is something that was found out actually here by Sasha last year, that if you have this current sheet, you can form these little magnetic islands. It's called the plasmoid instability. If you have 2 of these islands and they merge, they produce a radio signal. It's a very nice emission mechanism, and we can transfer this to the binary. So please keep this picture in mind, because this is going to tell us how the binary can shine in radio, ultimately. And then just 1 or 2 words. This is not particularly important. It's like how we do the numerics, because we have to solve a set of equations in order to model this. This is not possible to do analytically, at least the complete system. And so what we do is we solve the general relativistic form of Maxwell's equations. If you already didn't like Maxwell's equations, this is going to be worse. But the idea is you can kind of macroscopically describe the effects of this plasma in a simple current formulation that enforces that your electric and magnetic fields are always perpendicular, and you can enforce the speed of light condition, but like saying you cannot co-rotate faster than the speed of light by saying that E squared is less than B squared. The nice thing about doing general relativity, which in principle, in order to understand the basic physics, is not necessary. I mean, actually most of what we do is in special relativity, but the nice thing is if you do general relativity, you can go to a co-moving frame, because this thing is totally frame invariant. Then you get, just like your coordinates rotate and the stars do not. That makes things a lot simpler, and that's basically the mathematics take care of everything. And then what we do, we have to solve this in a code, and this is the code that I'm developing. This is a code that actually is used to do neutron star mergers. So what I'm doing is I'm solving the equation of hydrodynamics and Maxwell's equations. This code has fully dynamical AMR, so this shows you just like 2 black holes moving in an ambient medium. We can nicely refine all the substructures at minimal computational cost. And while I was here, I've extended this code to also do this force-free formalism in order to study exactly that process. Another thing that came out that actually wasn't planned, but nicely aligns with what I'm doing also for my PhD, is to connect what happens in the merger with plasma physics. So this is just like 1 slide of advertisement, what we're doing there. And so the idea is that all of these nice transients that I was talking about in the beginning, like the afterglow, the short gamma rebursts, I mean, they're fueled by magnetic fields. But we don't really know what the magnetic field is, because some simulations indicate that all of the magnetic field is produced just at the shearing when the stars merge. This is really like a very demanding simulation we've done with this tool in order to resolve all of the small-scale magnetic field growth. And here we have a nice collaboration going on with the Princeton Plasma Physics Lab, and together with Amitava Bhattacharjee and the other scientists there, we're currently looking into how we can model this dynamo in an effective theory, how we can understand how the small-scale field growth propagates to the large scale and then explains how the mass ejection and so on is driven. But that's not part of this talk, it's just a little bit side advertisement. Now, when we want to study this precursor, we kind of have, as I said, we wanted to have some kind of pulsed emission. So we need some mechanism in order to tap into an energy budget of the system, store the energy, and then release it. And so just to illustrate how this works, we imagine we take these two stars and we make one star spinning. So the right star here just acquires a spin. If we again draw our cartoonish field lines, what really happens with the field lines, if you look at this closed loop that you have here, and one of the stars is spinning, then you see that the magnetic field lines start to twist. So you're transferring energy from the rotation of the star into the field line, but it's really like spinning a rubber band. So you have the rubber band, you spin and you spin, at some point the rubber band will burst. And the similar thing happens here. At some point the magnetic fields will reconnect and they will release a ball of energy flying out, and this is then hopefully detected at some point by Tom and his colleagues in Caltech. And so just to tell you, we're going to now look at the simulation of actually how this works. But just to give you some idea, let's zoom in because we will look at the quite zoomed out version of the movie. We have the two stars. Here the magnetic field lines are in white, they're pointing down. On the right, they're pointing up. And in color, we show the in-plane magnetic field. And so while this right star here is spinning, you build up a twist in the magnetosphere, and this is shown in color. So whatever is in color, view this as energy put into the magnetic field, and at some point you see that something will happen. I'll just play the movie now. You see, right star spinning, we transfer energy into the field lines, and then a burst, like a magnetic bubble, is being ejected, and has this trailing current sheet that hopefully roughly reminds you of the simulation picture that we saw in the beginning on how we can produce these nanoshots from the pulsar. And so what we did is we studied a bit in more detail how this works and what are the observational prospects of this. If you look at the energy, when you think of our initial estimate, we find that by doing this pulsation, we can burst the energy extraction by almost 2 orders of magnitude at peak luminosity. This is like a 3D visualization of how this fireball actually looks like, because it's not just like a bubble going up, but because it's also spinning, you have a lot of twist going on there. And then we went on to look at how does that look at the large scale, because if this is just a beamed emission, we have almost no chance of seeing it, right? It will just go in one direction. But the nice thing is that this flare on large scales is going to open up, so you expect something like an almost quasi-isotropic emission. You can best see this here. This is still pretty close. If you go further out, you see this becomes even more isotropic. And the nice thing is this reminds us quite a lot of a magnetar model for FRB. So you have some phenomenon in the universe where you detect fast millisecond radio transients, and one model to explain this assumes that you have this kind of synchrotron maser emission from such a bubble hitting the ambient plasma. So we're pretty sure that this is going to kind of create some radiation. I'm not going to go into many details of how much this is. We kind of estimate it might just be too low, but that depends a bit on the binary parameters here. But at least that's one of the emission mechanisms. The other emission mechanism that we have is this current sheet. And in order to understand this, we have to do a little bit of a finance accounting. We have to say, okay, what is the energy that we have stored, and what is the energy that is kind of lost? And we can use Poynting's theorem. So this is just what your energy equation would look like in special relativity. And so what we do is we say, okay, the bubble is ultimately going to be launched here, and it's going to propagate out. And so we're going to check what is the energy lost in the system, and this will be the energy that's dissipated in the current sheet, and that can then cause these nanoshots to be produced. So we just do a simple accounting. We look at, okay, the bubble has at some point to go in here, it has at some point to leave, so we take this into account by looking at this Poynting flux. We look into the local change in energy in this shell around the binary, and then we say, okay, whatever is not accounted for by propagating in and out again has to be dissipated in the current sheet. And so we just do the simple accounting. And really what I mean by the current sheet are these kind of islands that we form here, because they really dissipate the energy and cause an observational radio mechanism. And then we see that we have a very nice linear dissipation going on. What that tells us, if we look in terms of luminosity, I'm almost done. What we look in terms of luminosity is that the energy dissipated in the current sheet is about an order of magnitude less than the energy launched in the bubble, but this is still a significant fraction that we have. We also checked what the effect of the separation is, and we found that this has a very nice a to the minus 3/2 scaling. This basically will be modified if we add GR to the picture, because this was just taking two neutron stars and having them orbiting on a constant orbit, but in principle at larger separations that's a pretty good assumption, so we still believe the scaling to roughly hold. And finally, this is a very artificial picture, because as we said, we have pulsar detections, and so we know that the neutron star magnetic fields are not aligned with the orbital axis, but in general they will be misaligned and the spin will be rather slow. So imagine we have absolutely no spin, but now one of the magnetic fields here does not align with the orbital angular momentum. If we again draw our cartoonish picture, we see that once we go around and the star does an orbit, now the magnetic field points to the right, right? And so this means that if we have the field lines, there will be a twist caused just by the orbital motion. And so now instead of tapping into the rotational energy budget of the star, which might be small, you tap in the orbital energy budget. And that's a very general kind of concept because that will be always there irrespective of what your binary parameters are. And then we can perform exactly the same kind of simulation, and you will see, although this is kind of a not optimally chosen plane, that we launch the exact same kind of flare also from the system. And this is why we expect that even though we have a variety of parameters in the binary, we might, for certain cases, always get this kind of flaring event close to merger. And so in conclusion, just to summarize, I mean, we studied these electromagnetic precursors, in particular flaring events launched just before merger. These were caused by storing energy in the twisting of field lines. This is really like using this laser and storing energy for a pulse to boost the power temporarily, at least. And we found that this has two emission channels, one coming from this bubble really being emitted, really like a bunch of energy flying out, and in addition, the current sheet dissipation. And so what remains to be done, I mean, a regular talk would end here, but I think it's nice to say what we can further work on, and this would be to look a little bit more into the parameter space, to think about, can we provide an analytic fit formula? So if you were to detect such an event, can we invert this and say, okay, given a certain detection that we make, what was the spin of the neutron star, the orientation, and so on. For this, we also have to do full general relativity, and the nice thing is, I mean, my code has full general relativity and hydrodynamics in, so we can just combine it and do the full picture, like really the full merger. And if we can do this, we can also do black hole neutron star. In fact, we have tried. There are some issues, but I hope this is something that we get done soon, because the nice thing about the black hole neutron star is you have certain amounts of parameter space where just a neutron star is swallowed, so there's no matter left. You will not get a kilonova, you will not get a short gamma ray burst, but the precursor might still be there. So this is a nice window. We have to look into it. So thank you.
Thank you very much. Questions?
So you were mostly looking at this case where the magnetic fields of the two neutron stars were anti-parallel,
yes.
So you had field lines connecting. Will
exactly.
you always have lots of field line connection, or could you have...
I mean, this would work as long as you have some part of the field that is reconnecting, so that is like connecting. Because if you don't connect, you cannot build up this twist. I mean, these configurations where both would point in the same direction, they would not give you a lot of observational prospect.
Is there some indication of
no.
which regime we might be...
The problem is, I mean, you have absolutely zero indication of what the alignment is. You also don't know, this is really why this is interesting, you have not a really good clue even what the spin is. Even from the gravitational waveform, it's a bit degenerate in spin, so we don't even know that. This is where this could help.
How efficient is that last mechanism you talked about, where they're not anti-aligned and you're extracting the energy from the orbit instead, compared to the former one?
Compared to the former one, I mean, this is a number I cannot tell you yet because we're still working this out. The issue is if you have this misalignment, it's a bit harder numerically to extract what's going on, because if you take a fixed shell like we did, the field is constantly moving in and out. So we're still doing the analysis on this one.
So you can't say if it's 100 times weaker or the same, or...
I can't say yet, but what I can say is that the same kind of mechanism applies. Yeah.
So I had 3 questions, and now 2 of them have been asked. So that's great. I guess the third comment that I had is that Dan D'Orazio looked at the fireball mechanism for black hole neutron star mergers with Gen 11 in 2016. And she and I actually looked at this case here, where you have the neutron star black hole mergers and how you get a fast radio burst from it. And you're right that it's if you have a black hole, if it's larger than 7 solar masses, the neutron star is black hole. So this could indeed be the only kind of electromagnetic signal that you get out of that kind of system. So I think it's really interesting. And I'm also really interested to see what you and Sasha come up with numerically, because our estimates are in the
Yes, absolutely. I mean, the nice thing is you would have, in my opinion at least, you would have a similar twist than you have with the spinning star, because now you have a spinning black hole. So in principle, the same mechanism should also work.
Yeah,
yes.
Very interesting.
David?
What frequency should the radio astronomers look at?
That's a good question. I don't have the number out of the top of my head.
Is the question what should we look at, or what do we?
No.
That's a good question. Don't know the issue.
No, should isn't easy.
No, I'm saying.
Could is easy, you know.
Yeah.
But thinking like, as we look towards multi-messenger astronomy, I'll put my hat on as part of the Cadle survey, thinking about what kinds of things we want to make sure we're doing in the coming decades. Should is useful as well as what we can do right now.
And related to that, is it hard to predict the electromagnetic? Like your calculation is very freshman physics-y with the E squared plus B squared, but is it hard to predict what the radiative processes are?
So the nice thing is there have been a lot of advances in the emission for pulsars. So we do have a nice grasp of what the dissipation is. Also, if you ask in terms of numerics, the nice thing about the plasmoid instability is that your dissipation rate becomes independent of the actual resistivity. So even though we have a simplified approach with numeric resistivity and everything, actually that number should be roughly meaningful. But we have to check this in more detail, and Sasha has a very nice peak simulation of really taking the particle dynamics into account. And this will come next, and we will compare how the local peak simulation compares to the global picture.
Yep.
So a question in the similar vein. I think this was on the x-axis of one of your plots, and I just missed it. But when should we be looking? At what point?
I mean, the issue is really that, even though this is emitted before the merger, as you know, the signal has to travel through the ISM and through all the other material. So that really will influence the time at which this is delayed. What I can certainly say from the numbers, I think the only really time in this emission process will be the last orbits. Otherwise, your field strength when you have the interaction goes down, as we've said, a to the -7/2, and then you really go out of the range where you could produce anything. So I would really say last 2 orbits plus then the delay by.
Okay. So in terms of time, relative to the gravitational wave merger, we're really talking about milliseconds or something before.
Could be. I've tried to find some numbers on this and to discuss with other people, but could also be even a bit later, like a few minutes afterwards.
All right, let's thank Elias again. And our last speaker is Lily Zhao, whose home institution is Yale, and she's been here working with Megan Bedell and Hogg. Please.
Great, thanks, Chris. So my name is Lily, and I've had the great privilege of working with Megan and Hogg here, and also this long list of people on EXPRESS, which stands for, and I believe is, an extreme precision spectrograph. EXPRESS is designed specifically to find smaller planets by the radial velocity method than we have before. So just a brief recap, the radial velocity method, or the wobble method, takes advantage of the fact that in a star-planet system, they're actually both orbiting around their center of mass, which is denoted in this greatly exaggerated GIF by the X there. And so while this planet is orbiting, the star is moving a little bit too. And we measure that movement as a Doppler shift in the stellar spectrum here. And so here, as a function of time, you can see that the velocity changes as the orbit changes. And if you have a larger or closer in planet, that curve will be larger. And if you have a smaller or further away planet, that signal will be a lot smaller. And so here I have plotted the discoveries of RD planets by year as a function of mass. And you can see we did pretty well for a while, right? In 1995, the first planet around a star like Sun was found through the radial velocity method around 51 peg. And the interesting thing about that planet is that actually the hardware, the instruments that were capable of detecting such a signal had existed for years before the discovery. But no spectrograph had been calibrated well enough to get data that people believed were from a planet. And so that was a momentous discovery, and we've built better instruments since then. We've calibrated them better, and we've found smaller and smaller planets. But even though the trend was that way, we've still stopped short of finding a true Earth mass planet using the radial velocity technique. These are a lot closer to their planet. They're kind of cheating a little bit. But to find an actual Earth at the distance the Earth is from the sun, around a star that is the mass of the sun, what you need is an RV precision of 10 centimeters per second. So that's the number that everyone who works in this field right now wake up screaming when they have nightmares. So working towards this goal requires innovations at all different levels of the pipeline, right? We look at the star and we need better instruments, greater stability in these instruments to get good raw data from them. And when we have the raw data, we need better data pipelines that return the high fidelity spectra we need so that we believe the results that we're getting. And once we have that spectra, we need better ways of modeling it so that we get the RV signal out, and just the RV signal to get the RVs of the planet to tell us that a planet is there. And so through my talk, I'm going to highlight the different steps that we're taking with Express and doing with people here to achieve these different goals. So I'll start with instrument stability. And I know people here aren't maybe the biggest fan of instrumentation, so I thought I'd give a brief introduction.
We're big fans, just don't have to.
Yeah, we appreciate it.
So I thought I would go through some instrumentation basics, like Express is in a shell spectrograph, which is denoted by this shell grading, which is a special kind of grading that has the benefit of being able to separate spectral features wider. So you get more separation between different spectral features, and this allows for higher resolution, so you can detect more features in the spectrum. Right, so the light enters here, it hits a concave mirror, and the light beams come out parallel to each other. It hits the shell grading, which separates it into the different wavelengths, goes through another fancy optic thing, and gets separated into the wavelengths in this direction. And then it goes through another prism, and you can then separate the wavelengths again in this direction. So we have it going in both directions. So here's a picture of Express, so shiny. It's an environmentally stabilized spectrograph, so nothing should be moving, the temperature isn't changing, the pressure isn't changing, we're trying to keep everything the same. It has a high resolution of an average of 137,000, and it's an optical spectrograph, so it ranges from 390 to 700 nanometers, and it was commissioned in 2018. So if you take a look, right, we have our entrance slit, so this is where the light's going in and the fiber input here. Just like in the diagram, there's a concave mirror in the main collimator over there, which is hits. The light then goes to the shell grading here, which costs more than my childhood home, which was fun to learn. It bounces off some other optics that don't matter in this case, but another mirror, it goes through these prisms up here that separate the light in the cross dispersion direction or this way, and finally enters our detector. And when it does all that, we get an image that looks like this. So this is a raw image from Express that Express took a 51 peg, which was the star that the first planet was discovered around. And though I mostly made this image to flex a little bit, I will use it to point out some important features of the spectrograph. So one, you'll notice that the light is separated into these bands. We call them orders. And this is what happens when you separate the light in the cross dispersion direction. So it goes from blue to red in this direction. And they're also curved along the detector. So part of the data processing is you have to find out where they're landing, right? The curve of them on the detector, and then also the specific wavelength, so the color that each of these pixels represent. You'll notice the dark bands are the absorption features, and they're all rectangular because the slit that our light goes through is rectangular. And it's mostly vertical, which is by an extreme amount of design and alignment. Because they're vertical, that means that every line roughly falls on the same column of pixels. Because if they didn't, right, and they were tilted slightly tilted, there we go, slightly tilted, then one pixel would have a wavelength contribution from one wavelength, like 30% of that one, while it's mostly the other one. Then it would go to the main pixel, et cetera. And so that would add a lot of issues to it. And so finding the colors to make this look right is not as easy as it sounds. And the last thing I wanted to point out is that each pixel in this detector is roughly the width of 9 micrometers. And each pixel is, on average, a shift of 500 meters per second. Which means that when we say we want to measure a shift of 10 centimeters per second, what that's equivalent to is measuring a shift on this detector, roughly the width of 9 silicon atoms. So it's hard, and that's where you guys come in. All the statistics and data processing that has to go into it. But just a little bit more on the instrument first. So Express has what's called a laser frequency comb. And what it does is it produces these series of lines on the detector. So this is each order. This is the x directions, which is also wavelength. And you get one every 14 gigahertz, which roughly translates to 0.1 to 0.2 angstroms, which is every 10 to 20 pixels on our detector. And so this gives us a measurement of wavelength at all of these places, right? But we can also use it to measure how stable our instrument is, how well that's doing. So if we took a series of these LFC exposures and just shot it at our instrument one after the other, right, then the only thing that should be changing are things intrinsic to the spectrograph. And so if we do that and we take 30 consecutive LFCs, we get this beautifully flat line here, at least I think so, with an RMS of 3.84 centimeters per second. So what this says is that the instrument is there. We've done it. This is less than 10 centimeters per second. We have the instrument to measure the signal we need to find actual Earths. But when you go from the raw data, right, all the way to stars on sky that are noisier, that have clouds in the way, that have the atmosphere in the way, you get a formal RV error of 30 centimeters per second at an SNR of 250 instead. And so how do we take this 4 centimeter per second RMS and translate it to the best error we can get on sky to get the data that we need to find planets? One of the things is building a better data pipeline, which involves a lot of different things, but I'm going to focus on the wavelength calibration. So that's the process where you take each pixel on the detector and you figure out what wavelength corresponds to that pixel exactly. And if you get it wrong, it might look like a spurious RV shift, right? And then you're going to say you found a planet and no one's going to believe you. So this is classically done with just a whole bunch of polynomials. So you get a polynomial in the pixel space. You take all the lines, like every one of those LFC lines you saw before. You find where it is in the pixel on the detector, and you match it to a wavelength. And then you represent this relationship by a polynomial. So my group has been using an 8th degree polynomial to measure this effect. And so you do that for all of the calibration images you have, all the LFCs or whatever else you have. And you get a polynomial, you get these coefficients, and then you take the coefficients and you get another polynomial for them with respect to time. And so now you have the second polynomial, which we use a 3rd degree polynomial to kind of estimate what sort of changes your spectrograph is going with respect to time, which would affect the coefficients that you get for the wavelength relation. So you then use that, you get the coefficients for that particular exposure, and you get new wavelengths for that exposure. So work that I've been doing here has been expanding this process to both a hierarchical and non-parametric model that we've called Excalibur. Thank you, Megan Bedell, for that. And the idea is that we're taking all of these calibration exposures and we're doing it with an extremely stabilized instrument by design. And so we want to go to the hierarchical mode because since it's so stabilized, every calibration image you take should contain information about all of the other calibration images you take, and not taking that into account would just be throwing information away. And we also think it's high time that we move from a parametric model to a non-parametric model, because now we have these wavelength sources that are just full of lines all over the place. And so this allows us to fit other wavelength solutions than polynomials that enforce this kind of smoothness that might not necessarily be there in the data. So I'll go through, hopefully briefly, the process that we've come up with. Where first there's a bit of data setup. So we take the exposure, we find each single line in that exposure, and we add it to this long list of all the lines that we have. And each line is associated with an order that it's found in and the wavelength that it's been assigned based off of what we know about this laser frequency cone. We can then find the line centers that are associated with all of these lines in each of our exposures. So for each exposure, we have the same order and wavelength line list, and we assign it X value, so where it is on the detector. We then use TCA to represent this and apply a bit of denoising. So what's pictured here is that X value here on the X-axis versus exposure number I on the Y-axis. And you can see that as you go up, there's some shift in where the X value falls along the different exposures, but not too much, right? And so if you run PCA on this and you pick some low number order of the number of principal components you believe in, those principal components should capture the greatest amount of variety that's happening along these different line centers, like how they're shifting and things like that. And the idea is that they're capturing things that are actually happening in your spectrograph. Like if the temperature changes a little bit and the detector is moving or expanding or shifting back and forth, that'll be captured by the first few principal components, and the rest will be noise. So if you focus on the first few principal components and discard the noise, you get these noise line centers that uses all the information from all the calibration exposures that will be better than any measurement alone, which could have some error, which could be shifted somewhat because the line is missing, or the black lines here are lines that are just missing. So from that exposure, we just didn't have that information at all. And so we get these principal components, and we use it to find denoise line centers denoted by the star. Okay, so then we interpolate the different amplitudes for the principal components, so how much each of those variations apply to a given exposure in time. And so over here, we have time on the x-axis and the different amplitudes. We happen to focus on the first two, which are shown there, and how they're differencing with time. And so, for example, this big spike here corresponds to when those lines all shifted in the previous plot. And it's interesting to note that we did this both with the LFC and a secondary calibration source we have, a thorium-argon lamp, which has set lines due to atomic physics. And they actually trace the same behavior, which is a good check that this is actually measuring things that are changing in the spectrograph. So if we can interpolate what amplitude we'd expect to see at a different time, we can use that to figure out what line centers we should see for that exposure, and therefore get a calibration source for that exposure. We can then take all those denoise line centers, which is now plotted here, and interpolate between them to get a wavelength solution for any of the in-between pixels. Okay. So the classical method only did these two steps and used polynomials for absolutely all of it. And we're here incorporating much more of the other information that we have. So as a first test, we wanted to make sure that interpolating in X was the right thing to do, that we weren't introducing other noise, or it wasn't like a reasonable thing to do. And so we ran this test where we took all the lines in exposure, and we had the even ones predict the odd ones. So we either used the even lines in exposure to fit a polynomial that we then used to predict the odd ones, or the other way around. Or for the parametric one, we used the even ones to interpolate a solution and guess the odd ones, right? And so you can see that here, when you use a polynomial, there's a lot more residuals, and there's even a structure to the residual that we've determined have to be true to the detector, because there's no relation on wavelength or anything, only position on the detector. Whereas in the non-parametric case, that residual is gone, there's no pattern, and you get lower residuals, and they're more close to zero. All good things, right? And so believe that non-parametric is the way to go. It captures real structure on the detector and gives like more reasonable results. The next thing we wanted to test was like the interpolating in time thing, making sure that if you interpolated the principal component amplitudes, you get a realistic representation of what the spectrograph looked like there. So what we did is we have a training set, right? Like the calibration exposures we use to get those amplitudes to tell us what the spectrograph is doing. And so if we use those to guess the wavelengths of an exposure in the training set, we should get the limit to how well we can do. And so when we did that for the LFCs, the histogram of the residuals is here in black. And if we did that for the thorium-argon exposures, the other calibration source, the histogram is there in black. Now, if we separated out 10% of the LFC exposures, pretended we didn't have them, trained the principal component analysis on the remaining 90%, and then guessed it for the remaining 10%, you get this histogram in blue, which kind of just looks like an average talented child try to color in the black one, right? So I think it's doing pretty good. And even better, when you don't use LFCs at all, and you take them and you try and guess the thorium-argons, which are completely unrelated, different light source, you get the same result. The blue still looks like the black one. And so the interpolation in time is clearly doing its job in truthfully representing what the spectrograph looks like at that moment. And so if you compare them, the parametric polynomial one is the blue. If you just go to a non-parametric where you interpolate instead, you get the green. But if you incorporate all the information that you have from all the calibration exposures, you get the orange curve, where the median is even closer to zero and the residuals are all closer to zero. I'm going to say that job is done then, and move on to data modeling for now. And for data modeling, I've been working with Megan here on implementing Woblet, per code, which is a data-driven method for extracting RVs while also modeling what the spectrum should look for. And so the model is defined by this, where your observed spectrum, y sub n, is a combination of what you're seeing from your star, y sub n star, and what you're seeing from the atmosphere, so tellurics, y sub n t, and also some noise. And so the stellar spectrum should just be represented by a nominal stellar spectrum, what the star looks like, shifted by the velocity that you're measuring. Whereas the telluric spectrum will be this nominal telluric spectrum, so what the atmosphere looks like at the time, plus some variability depending on how much water is in the air, things like that, and multiplied by an air mass, how much of the atmosphere you're looking through. And so I'm doing this to flex a little bit again. I want to show RVs for 51 Peg, the discovery of the first exoplanet. So this is the data set which the discovery was based off of, which the Nobel Prize was given for. And if you overplot Wobble RVs, you can see that it's following the model a lot more closely. And there are, in fact, error bars on those points. They're just so small you can't see them because the points are too big. And if you compare the results from Wobble to the different methods, so for example, a CCF method, which is typically used in the field, or chunk by chunk, which is like a forward modeling technique, there's a lot less scatter, and the blue points in the CCF, like where the blue points from the CCF, where their scattering represents largely exposures with lower signal that it couldn't really deal as well with. And the scatter over here with the chunk by chunk is when there were a lot of tellurics that it couldn't deal with. So things that are addressed by Wobble's like all-inclusive modeling, where it takes into account both what the stellar and telluric spectrum should look like, and uses the information from all the exposures. And so because Wobble also gives you this model of the star and the tellurics, right, you know what your star is supposed to look like. And so when you have other signals in there that are messing you up, like stellar activity, things from the atmosphere, things like that, those will be missing from the models that you get from Wobble. And so the next steps would be using these models to determine what things are different about what we expect to see and what we actually see. And those will be a measurement of the noise sources that everyone's trying to get rid of, the ones that are clouding our ability to find Earth-like planets. So in summary, I told you we had to fix the instrument stability. I think we're most of the way there. I told you that we had to work on a better data pipeline. And so here with David Hogg, we constructed a better wavelength solution that's a lot better than what people have classically done. And I told you that we needed to model data better, and we're getting started on that by applying Wobble to Express and using the models there to disentangle other noise sources from the RVs that we're getting. So CCA has done a lot for us and the Express team, and I hope to continue working with you guys in the future. Thanks.
Lily? Any questions? Sigurd?
So in that last plot there, where you have those points with invisible error bars, I guess that means that the deviation here is actually super significant. Like there's a point there that's probably like 20 sigma away or something, considering the size of the error bars. Would that be like the stellar, unmodeled stellar physics and weird stuff going on, or?
Exactly, yeah. So it would be stuff like the stellar atmosphere moving in or out, or like spots around the star contributing a radio velocity signal that isn't due to the planet.
Okay.
And so that's exactly what we're trying to measure using the Wobble models to get rid of the stellar and telluric components.
There was one thing I was a bit worried about with the is time interpolation. Because you had these things where you had this sudden jump in the position of the pixels, and it looked like basically linear interpolation was being done there. And probably what's really happening between the sudden shift is not that it's just smoothly going to the shifted position and then smoothly going back again, right? Probably it's, so I wondered if maybe the errors had some sort of non-Gaussian distribution where the core is really nice and tight, but then due to rare events like this, you have this. Maybe that could be what's going on with that that outlier point.
Yeah, that's a good point. So we actually mapped that jump to a temperature shift in the spectrograph.
Okay.
And so actually the linear interpolation does do pretty well, because locally the spectrograph will always vary basically linearly. And so if we take enough calibration images, linear interpolation is sufficient. But because we know that these huge jumps are due to temperature shifts in the spectrograph, which is something that we measure, a better thing to do would be to interpolate with respect to time and this temperature spectrum, which we have like much more densely sampled data about and would be able to model much better.
Yeah. Yes, that was my question about how, so what I think of is housekeeping data, where you're monitoring the temperature and other properties of the instrument. I thought about folding that in, particularly in the context of higher kind of denoising model, it seems to be sort of natural to stick that additional data into the model.
We have, and there's 2 weeks of the fellowship left, so.
Good.
I guess I have a similar question for the, 3.5 centimeter per second drift on the instrument. So is that the fundamental limit, or is that something you get around with data modeling? And just to give you the context, this is coming from people in the galactic community and actually other communities thinking about gravitation, galactic accelerations, which a little below a centimeter per second.
Okay.
So if we could go down a little bit.
Oh, 10 centimeters per second should be enough. So the 3.5 RMS is like technically, I think, the lower limit of how well our instrument can do, just because like any signal underneath that would be masked by any noise from the instrument. But I feel like if you asked David Hogg about it, he would come up with something about how data can fix everything and everything.
Yeah, so I guess that is my question. It's so close.
I don't think that limit is fundamental, but I do agree that it's hard to beat, because I believe you're showing like really simultaneous LFC exposures. So it's very short timescale variation. So I don't know. But of course, we can take many observations per star, and if it is uncorrelated on long timescales, then I mean we can always do root n. So in that sense, it's not. And the galactic acceleration is
many stars in a single location. Does that help you?
Yeah, and we can correlate stars. Yeah, there are some ways you might be able to measure them.
People are starting to write papers on this, right? As you know, and other people are thinking about it.
That's a great question.
Okay, so now in a few minutes we'll reconvene. We have a reception in the common area and have a short toast or ceremony. And first, let's thank all of our Predocs again for